Hello everyone, today I will be presenting to you the preliminary results from a landslide susceptibility analysis using QGIS for Northern Kenton County, Kentucky. QGIS is a free and open source software available to download and use. The maps in the slides show an overview of where Northern Kenton County is located, highlighted in red and in the bottom right map. Kenton County in general is located south of Cincinnati, Ohio, shown in the bottom right inset. Zooming out, we can see that Kenton County is located on the northernmost tip of Kentucky, highlighted in orange in the top left map, which is a part of the contiguous United States, shown in the small top left inset. There are three water bodies that run along or through northern Kenton County, shown in blue, called the Ohio River, the Licking River, and the Bank Lick Creek. I chose this study area because Kenton County is known for its landslides. It is important to know that I am only studying the northern half of Kenton County because the county is very large in length. I decided to confine most of the research towards the more urbanized areas located north of Route 1303 and south of Cincinnati, Ohio. To give a brief overview of what to expect in this presentation, I will first be discussing what landslides are and the main factors that cause them. Several characteristics such as topology, geology, and climate will depict the profile of the study region. As a precursor to the preliminary landslide susceptibility analysis, a supervised classification was conducted on two Landsat images from 1988 and 2016. The findings of this analysis and how part of the results served as an input into the preliminary susceptibility analysis, which will be discussed in further detail. The presentation will conclude with some general conclusions, a discussion of the limitations of the study, and what future work could be done to further improve the analysis. What are landslides? An example of a landslide is shown in Figure 2, where you can see soil and some trees have toppled over along a sloped landscape. Luckily in this area there are no roads or houses present, but you can understand how landslides may present a very real danger and cause damage to these structures. According to the Planning and Developmental Services in Kenton County, cost estimates of damage and repairs tabulated to a lofty $37.4 million over a 7-year period. Not only can landslides cause damage, but it can happen in an instant with little preparation, therefore making some landslide occurrences life-threatening. In addition, landslides can force people out of their homes and make a once habitable area now temporarily or permanently uninhabitable. Landslides occur when rock and soil move downwards, due primarily to the influence of gravity. Unfortunately, gravity is not the only factor that acts alone in causing landslides. In Kenton County, it is primarily a combination of geology, soil type, and slope that make areas more prone to landslides than others. Other factors that can contribute to the occurrences of landslides are human activity, heavy rainfall, and changes in water level. I will be discussing each of these factors a bit more in detail in the upcoming slides. In Figure 3, there are an array of different types of landslides that can occur. I won't go over all of these types of landslides in detail, but it is worth noting that there are a lot of types and each has its own set of factors that cause it to occur. For example, landslides that flow, such as debris flow, earth flow, slump earth flow, and debris avalanche are categorized based on the velocity of the flow and the type of material associated with it. Flow velocities that are slower and consistent of clay soils atop sloped shale can result in earth flows. Faster flows velocities with larger soil and debris size, as well as steeper slopes, can result in debris-related flows. One major factor of landslide occurrences is the geology of an area. The geology of an area can include the soil, bedrock, outcropped areas of bedrock, hilly and mountainous areas. These formations or layered deposited materials can be composed of many different types of rocks. In this case, shales are known to easily erode and can hold large amounts of water because they contain clay. In the Figure 4 presented below, there are the more common types of rock formations found in Kenton County. You can see here that between 500 and a little less than 750 feet above sea level is a large cope formation that primarily consists of bluish-gray shale. The Fairview Formation also consists of shale but is intertwined with limestone, another easily erodible rock when exposed to acidic rain. From this figure, you can see that majority of the formations or layered rock consists of some combination of limestone and shale, or of just solely one or the other. A second major factor in landslide occurrences is a combination of soil and slope. As previously mentioned, shale and rock formations tend to hold water due to their clay content. In soils, if high amounts of clay or silt are present, they can hold more water too. When these soils are located on steeper slopes with a shale-based bedrock, they are prone to sliding. In Figure 5, a comparison between LiDAR data, landslide observations from satellite images, and reported landslide occurrences showed that in both cases, more than half of the landslides occurred on the Cope Formation. From the previous slide, this formation is a more dominant formation found in Kenton County and contains bluish-gray shale. When taking into consideration the slope on which these landslides occur, Figure 5 shows that the average slope of all landslide occurrences, both observed with the LiDAR data, happen around 15.3 degrees with an approximate 27.4% occurrence rate. It is worth noting on the same slope degrees and slope percentage relationship diagram that a red line at 45 degrees means at this slope it is known that landslides will occur at 100%. The first of the three secondary factors previously mentioned is human activity. Human activity can consist of the following. The removal of vegetation such as trees, grassy area, etc. can remove important plant roots that provide support and structure for soils, therefore leaving them looser and more likely to move. Building structure that put weight on sloped areas can make these areas more prone to giving and resulting in landslides. In addition, runoff from these structures, which is circled in Figure 6, may cause seepage and cause an area to sink down due to the amount of water continuously being put into that location. You can see that with the road ditch infiltration circled in Figure 6. Leakage from pipes or other underground structures such as septic drains highlighted in Figure 6 by the red circle under the house can also affect the surrounding area and increase the likelihood of landslide occurrences. Mining activities, which can occur above or below ground, can make an area more susceptible to landslides. Heavy rainfall tends to increase the likelihood of landslides to occur. When rainfall increases, poor water pressure increases in the soil. As a result, this makes materials on sloped areas more susceptible to movement. You can see an example of this in Figure 7, where in areas that may have also experienced tree removal, heavy rainfall can result in water runoff and mobilize the sediment in soils to move. If located on a sloped area that contains shale, movement is more likely and, as seen in Figure 7, can fall from higher regions that may impact developed areas below, in this case, a house. Lastly, another factor is changes in water level. When groundwater suddenly decreases, the porous space in the media become empty and the pressure within that space cannot adjust properly and support the media. Therefore, the empty porous space within soil or rock are more likely to collapse, causing slope instability, leading to increased occurrences of landslides. Areas losing water to seepage, like in Figure 8, or groundwater withdrawal could experience this type of instability. As part of the site characterization of the study area, I have included the following GIS-related data. 30-meter resolution digital elevation model obtained from the USGS Earth Explorer site, a slope-derived layer from the DEM data, geology and soil layers for Kenton County from the USDA NRCS Geospatial Data Gateway, and annual precipitation and mean temperature data for 1988 and 2016 from the PRISM website. I chose a comparison between 1988 and 2016 because I was going to use a Google Earth image from 1986 for a 30-year comparison, but for the supervised classification, I wanted to use Landsat imagery data instead, which only dated back to 1988. The following map in Figure 9 shows the DEM for Northern Kenton County. From this map, you can gather that the highest elevations, 281 to 303 feet, are located towards the western and southern parts of Northern Kenton County, Overall, the entire area seems to be relatively high above sea level, ranging in 216 to 259 feet with sharp drops in elevation towards the center and northeastern parts of the county, and also in regions where water bodies are present. Here, we can see just how steep some of the slopes are in regions where the elevation has dropped significantly. These areas are along places where there is a river or a creek nearby. Steep elevations, symbolized in darker green and measured in degrees, can be mostly found in the north, northeastern, and eastern parts of the map. Some slopes are as steep as 58 degrees. That is very steep. Moving on to geology, we can see highlighted in red in Figure 11 the predominant cope formation. If you remember from earlier in the presentation, cope geology was where over half of the landslides have occurred in Kenton County. In brown is the Fairview Formation, which is a combination of limestone and shale. The Fairview Formation is another area prone to landslides, but not as high as the Cope Formation. The highest elevations are where the Bull Fork Formation is highlighted in green. If you look towards the eastern portion of the map, you will see symbolized in orange the alluvium geology, which consists of clay, silt, sand that is loose and unconsolidated because it formed from river deposits. Lastly, in the upper right corner of the study area, you can see two little spots from where glaciers left unconsolidated, undifferentiated deposits. I know this map is a bit overwhelming, but in summary of the soil types found in Northern Kenton County, just about all contain either a silt loam or a silty clay loam mixture. If you remember from previous slides, these two types of media hold more water, making this media susceptible to sliding down sloped areas, especially shale sloped areas. The main takeaway from this map is the purple areas that are Eden silty clay loam on 20 to 35% slopes eroded. This is significant because the purple area covers an extensive amount of the northern portion of the county, overlapping areas of known high elevation, steep slopes, and with underlying cope formation, all ripe ingredients for landslides to occur. Mean precipitation in 1988 to 2016 has increased by a range of 234 to 350.9 millimeters. Increase in precipitation over time could mean heavier rainfall events in the region. Heavier rainfall means more storage of water in clayey and silty soils and formations, thus increasing occurrences of landslides. The last characterization is the mean annual temperature shown in Figure 14. There is a marked increase of at least 2 degrees Celsius from 1988 to 2016. Increases in temperature over time could be attributed to global warming or climate change, or increases in urbanization causing microclimates in the form of heat island effect. To give you an idea of the workflow, I made a chart to walk you through the main processes in the analysis. First, I started with searching and processing the data. I separate the data into two different main workflows where I process the Landsat 5 and 8 images differently from the rest of the data. Data processing of these images consisted of merging two downloaded images from each Landsat satellite and merging them together. Once merged, I could overlay the polygon representing my study area. Initially, I had clipped the satellite imagery down to entirely Kenton County polygon. However, later on I realized it would be more beneficial to just limit the study area to the northern portion of Kenton County, since Kenton County is very big. I mentioned this previously, but just to reiterate, I chose the northern part of Kenton County to study rather than the southern portion because the northern portion is more developed with dense urban and suburban areas. Therefore, the landslides are more impactful to the population living within this region. Continuing on to the left, the next step for the Landsat data was to run a supervised classification. I go into more detail and provide an instructional video on how I classified the data. This was then followed by an accuracy calculation to determine how accurately I classified the Landsat data, followed by a comparison between the two Landsat time period, leading to the creation of the thematic land cover change map. After analyzing the results, I decided to use the classified 2016 Landsat data to represent urban and suburban areas as inputs into the landslide susceptibility analysis. At this point, I went back to the other data, which included geology, soil, precipitation, and slope to clip down to the study area and reproject into NAD 83 Kentucky Single Zone Coordinate Reference System, or CRS. Depending on if the data was a raster layer or a polygon layer, influenced how they were further processed. For polygon layers, an additional step of adding a binary column to the attribute table to then create the binary susceptibility index layer was done before converting the polygon layer to a raster. When converting to a raster, I was able to select the binary column as the attribute to be represented, thus creating the binary susceptibility index at once. For all data that was already in raster form, including the Landsat data, I simply reclassified the raster into a binary susceptibility index layer. The binary susceptibility index essentially ranked the attributes by a ranking system of 0 or 1 for no susceptibility or susceptibility respectively, or from a low to high number system of 0, 1, 2, 3, depending on the layer and its attributes. At this point, all data should have been reprojected into the NAD 83 Kentucky Single Zone CRS and then resampled to raster size cell of 30. The resampling was done to ensure that all raster cells aligned between the layers, since I would be using raster calculator in the next step to add all of the raster layers together. The final output raster was then reclassified and symbolized to represent the Landslide Susceptibility Analysis results. Both Landsat images were taken from the USGS Earth Explorer website. In the map presented to the left, Landsat 5 imagery data was downloaded for December 1988 and is showing bands 7, 4, and 2, which represent shortwave infrared, near infrared, and green. This band combination was chosen because it emphasizes urbanized areas in reddish coloring. Band 7 is known to brightly colorize urbanized areas, farmlands, and highways. Although a bit difficult to distinguish, the rosier reds are the urbanized areas and the orange-tinted reds are the forested regions, indicating healthy vegetation. The Landsat image to the right is from the Landsat 8 satellite for December 2016, with a band combination of 7, 5, and 3. This band combination mimics the same band type as Landsat 5 described above to emphasize urbanized areas in magenta coloring. On this slide are the results of the supervised classification for both Landsat 5 and 8 images. In the legend, you can see that subclasses were used instead of macroclasses and that I chose to use the maximum likelihood algorithm. The macro classes not shown here are water, developed, grass, and/or open field and dense forested areas. Just to reiterate, I use class ID because it gave a more detailed representation of the class type despite issues with band signatures overlapping for many of the class types. I chose the maximum likelihood algorithm because it gave the best representation of class types across the region. Based on the classification results, the biggest areas of change you can see visually between the two time periods are the reduction of forested areas and the increase in both urban and suburban areas. The once forested areas are now either open fields, suburban, or urbanized areas. You can also see that a lot of the suburban areas in 1988 seem to have changed into urbanized areas by 2016. After performing the supervised classification, I wanted to know how accurate my classifications were on the first try. I calculated each type of error based on a confusion matrix, not shown here, which verified classification results using Google Earth images from each of the time periods. Random points were generated for both classified images and the same points overlay onto the Google Earth image. From the confusion matrix, the following types of errors were calculated: errors of omission, errors of commission, producer's accuracy, user's accuracy, and lastly, overall accuracy. Producer's accuracy and the inverse percentage value, errors of omission, look at how well the model created by the producer identifies each class type. If the model identified the class type accurately, it falls under the producer's accuracy calculation. If the model identified the class type incorrectly, it falls under the errors of omission calculation. The user's accuracy and the inverse percentage value, errors of commission, looks at the probability the pixel was predicted to be a certain class type, and if it is that actual class type from a map user's point of view. This compares the number of correctly predicted pixels of a specific type of class to the total number of predictions of pixels for that specific class type. Lastly, the overall accuracy calculates all of the correctly classified pixels for each class type and divides it over the total pixel count of all classes. In Figure 17a, the calculated overall accuracy for the Landsat 5 supervised classification was found to be 69%, while in Figure 17b for Landsat 8 it was found to be 63%. To represent class type changes from one class to another, a thematic land cover change map was created. In Figure 18, to the left, is a reclassified version of the thematic land cover change map that shows no change in gray, all class types changed to urban in red, all class types changed to suburban in cyan, and all class types changed to open field in yellow. By categorizing changes in this way, you can see how much of combined classes changed to a certain class type. For example, red symbolized classes such as suburban, open field, and dense forested areas have changed to dense, urban class types. Based on the thematic land cover change map on the left in Figure 18, you can see that a lot of class type changes to urban areas with dense groupings in the northwestern, western center, and southwestern parts of Northern Kenton County. If you remember from earlier in the presentation, one of the other factors considered in landslide occurrences was human activity. Human activity in general can affect sloped regions by putting more weight than it can handle, by creating impervious surfaces that lead to runoff concentrations in certain areas and tree removal, just to name a few. With such widespread changes, do you think these areas are seeing more landslide occurrences than, let's say, in 1988? It is definitely worth thinking about. Before moving on to the next slide, I just want to point out the map to the right in Figure 18. The thematic land cover change map is overlaying a DEM to give some sense of location in terms of elevation to where some of the more concentrated changes have occurred. As previously mentioned, the highest elevation resides to the western part of Northern Kenton County. Do you see how most of the development has occurred also on the same areas of highest elevation located to the west? What do you think that means for potential landslide occurrences and how that may affect a greater number of people as opposed to less developed areas? All important questions to ask when considering how landslides occur and who and what they can affect in the process. The factors I considered in the landslide susceptibility analysis are geology, soils, slope, mean, precipitation, and supervised classification. For each factor, I created a binary susceptibility index, which I will explain in more detail shortly. Geology was a factor chosen because it was considered as one of the major factors that affect landslide occurrences. In particular, the Cope Formation was noted to have over 50% of all landslides occurrences and therefore was ranked highest in my susceptibility index as 3. The Fairview Formation was given a 2 for the second highest and alluvium as 1. All other formation media type was given 0 for no susceptibility. The second major factor was considered soil type. In this case, the data combined the type of soil with the degree range of slope it was located upon. Therefore, silty and clayey soils on slopes greater than 15.3 received a 1 for susceptibility, while all other soil slope combinations received a 0 for no susceptibility. In addition, slope was considered the third major factor that played a role in landslide occurrences, with average landslide occurrences happening on slopes of 15.3 degrees. As a result, a binary susceptibility index of 1 was given to all slopes greater than and or equal to 15.3, while all slopes less than 15.3 was given a 0. Two additional factors were considered in this analysis: annual mean precipitation and supervised classification, both data sets in 2016. Annual mean precipitation was considered a factor for two reasons. The first being it more accurately reflects the present conditions of rainfall amount annually. And the second is that annual precipitation has increased since 1988, which should be taken into consideration for this analysis. The annual precipitation range of 1,197 to 1,323 millimeters was broken up into three equal groups and labeled from increasing ranges of 1 to 3 for low to high susceptibility. Lastly, the supervised classification data was Landsat 8, 2016, was used to factor in susceptibility of urban given an index value of 2, suburban given an index value of 1, and all other classes were given 0 for no susceptibility. The reason behind including developed areas within this analysis is based on significant changes in development over time. Human activity is a secondary factor that could also affect landslide occurrences. Here I present two more examples of what a binary susceptibility index may look like for any given factor considered. In the map to the left, I show an example of the supervised classification for the Landsat 8 2016 image reclassified into the binary susceptibility index. The map on the right shows a similar example for the soil layers. I present to you the preliminary results. In Figure 20, I show the same landslide susceptibility results symbolized in two different ways. The reason is I couldn't choose which symbology scheme I liked the best. The map to the left, in my opinion, shows more strikingly to the eye, where dark red areas are more prone to landslides. Notice that these areas are where elevation drops suddenly from high to low. You can see a lot of the medium susceptibility areas are located from the center of Northern Kenton County to its north border. This is typically where majority of the urban and suburban areas are located, as well as Cope and Fairview Formation, the Eden silty clay loam mixture on 30 to 35 degree slopes, and as previously mentioned, steeper slopes, slopes greater than 15.3 degrees. This area also receives more rainfall than the southern portion of the study area. In the map to the right, I symbolized the map to a more traditional susceptibility map as instructed by my professor, Dr. Isaacs. Therefore, high was shown in red, medium in yellow, and low in blue for landslide-prone areas overlaying a DEM layer. Landslide data was obtained from the QGIS, Kentucky Geological Survey, landslide inventory data website, however, could not be directly downloaded into QGIS. To compensate for this, a layer was created based on overlaying landslide data points on a Google Earth image and then georeferencing that Google Earth image into QGIS. Therefore, the landslide data are very close approximations to where landslides have either been observed in the field to have occurred or have been spotted using LiDAR satellite imagery. A lot of the same regions highlighted in dark red in the map to the left and in red to the map in the right show a high number of landslides occurring in those regions. Being able to compare actual field results to the preliminary results gives confidence that these susceptibility estimates are relatively accurate. The preliminary results of this analysis take into consideration 5 factors, but of these 5 factors, 2 change more quickly with time: urbanization and precipitation. With population growth rapidly increasing, areas that were once forested are now being changed to suburban areas. Those areas that were suburban areas are slowly changing into urban areas. This means increased human activity, increased placement of structures, and increased changes to the land that will make areas more prone to landslides. In addition, we are now seeing a growing trend of increased precipitation in this region. This may be attributed to the global climate change. As global average temperatures continue to rise, some regions may experience extreme weather patterns, such as more droughts or heavy rainfall events. Precipitation plays an important role that can affect changes in underground water levels and runoff, both factors playing a role in landslide events. It is my hope that from this analysis we can build landslide susceptibility maps that could be used for local and state governments in planning projects, for homeowners who are looking for landslide-based insurance, and for insurance companies who are providing landslide-based insurance. These maps can be used to educate the general public on what causes landslides and the factors that make areas more prone to landslides. While this preliminary analysis showed a good correlation of susceptible areas to landslides compared to actual landslide occurrences, there are areas in which this analysis can be improved further. But first, let me discuss some limitations of the study. I think if we can overcome these limitations, then the preliminary susceptibility analysis will become even more accurate. The limitations of the study are as follows. Difficulty in locating a more detailed geological map that could give a more accurate depiction of where certain bedrock formations are located and could be used to identify landslide-prone areas better. I was able to download a 2-meter DEM, but due to processing errors at the time, I could not incorporate this DEM into my analysis. Was unable to directly download the landslide data, therefore the layer I created was based on approximate landslide locations and not exact locations. And lastly, I could not find an accurate river or stream layer to use. Suggestions for future work to improve this analysis could be to include hydrological, flood-prone areas, watershed, and/or more accurate river data. To use the 2-meter DEM and derive the slope layer from it. Either redo the supervised classification of the Landsat 8 image so that there is a higher accuracy result, or use an available land cover map, and redo the analysis with 2018 for precipitation and Landsat 8 imagery data. I hope you have enjoyed my presentation, and if you are interested in reviewing my references for data sources, I have provided here on this last slide. I look forward to your comments. Thank you very much for watching.